Får du med? Yes, fint. I'll be speaking in English just to keep you all awake. It's not only Netflix that speaks in English, scientists do it too sometimes. Yeah, my name's Ian Salter. I'm a chemical oceanographer based at Havstovan, and I was asked today to talk to you about ocean acidification, which has found the name Miðalsúrleik sjógvi in Faroese. And this corresponds to Sustainable Development Goal 14, life below water, and it specifically refers to one of those 158 indicators we were hearing about earlier, which has got the catchy name of 14.3.1. And it refers to average marine acidity measured at an agreed suite of sampling stations across the globe. Ocean acidification is sometimes known as the other CO2 problem. It has the more poetic phrasing in English of the evil twin of global warming. Evil twin because it's probably less well documented or at least known about compared to global warming, the rise of temperature. But a twin in the sense that it's something that's brought about by increased concentrations of carbon dioxide in the atmosphere. And I think given that, it's important to just quickly revisit the scale of the changes we're talking about here. There is still some skepticism about this. What this graph shows is the release of carbon dioxide into the atmosphere through the combustion of fossil fuels and changes in land use since the start of the Industrial Revolution in 1850. So fossil fuels is grey on the graph there. And you can see the sharp increase in that release, and it corresponds to around 35 gigatons of carbon dioxide per year at the moment. That's 35 billion tons of carbon dioxide. And that, of course, that manifests itself in an increase in the concentration of atmospheric CO2, and that's been reported from observations. So this is perhaps the most famous observation series that documents that. It's known as the Keeling curve. It's named after the scientists who established this atmospheric observatory based in Hawaii, which measures atmospheric CO2 concentrations. And you can see this sharp increase from when these observations began in 1965 up towards present day, going from 320 parts per million to over 400 now. It's even higher than that now. It's also possible to reconstruct carbon dioxide in the atmosphere over longer time scales, and that's important to understand the natural variability of the system. This is often another kind of criticism that you hear, that it's just part of the natural variability. And you can do that by examining ice core records. So if you drill down through ice cores in Antarctica, you're effectively drilling back through time. The deeper down you go, the further back in time you go. And those ice cores can be dated through looking at layers of ice formation, but also using isotopes. And when the ice forms, it traps little bubbles of air in it. And these act as kind of time capsules because they preserve the conditions of the atmosphere at the time they were formed. So you can analyze the CO2 concentration in these little air bubbles, and by doing that, you can reconstruct records back over time. So this is one example of that going back 1,000 years only. And you can see that CO2 was relatively stable at a pre-industrial value of around 270 parts per million, up until the start of the Industrial Revolution, when you notice a sharp increase. You can go much further back in time, and this record from the Vostok ice core extends back almost 500,000 years. And this is an important record because you can see the cycle or the variability of CO2 in the atmosphere over this kind of 500,000 time scale. And this variability, which is on the order of around 80 to 100,000 years, corresponds to these glacial and interglacial periods in the Earth's climate history, or ice ages as they're sometimes referred to. But you can see even within these, and these are triggered by changes in the orbital parameters of the Earth, and then they're amplified by oceanic processes on the Earth. But you can see even within this large natural variation, we're still only dealing with fluctuations on the order of 80 parts per million, so from around 200 in glacial periods to around 280 in interglacial periods. We're in an interglacial period now, obviously. And that corresponds to this pre-industrial value of around 275, 280 parts per million. The red line on that graph shows the increase since the start of the Industrial Revolution. So you can see that it's just completely dwarfing anything that we've measured before. And I think what's important here, it's not so much the absolute value, well, that's alarming enough that it's so high, but it's the rate of change which is important here. It's a sharp increase, a vertical increase. And that makes sense, because if you think about it, this has come from burning fossil fuels. Fossil fuels take millions, if not tens of million years to form. And this amount of carbon's being released into the atmosphere over a timescale of a few hundred years. So there's a huge perturbation of these natural cycles of the Earth system. So what's happened to all this CO2 in the atmosphere? About a third of it has remained in the atmosphere. That contributes to global warming through the greenhouse effect, changes in the radiative balance of the atmosphere. About a third of it has been taken up by land plants, and about a third of it has been dissolved in the ocean. So what happens when carbon dioxide enters seawater? The short answer is that the pH decreases, which is where this term ocean acidification comes from. It's worth just revisiting what pH is. Everyone's familiar with pH, but it's actually it's a scale that goes from 1 to 14, but you'll notice from this equation on the board that it's a logarithmic scale. That means for every change in one pH unit actually corresponds to a tenfold increase or decrease in pH. So that's important to remember, because when we're talking about ocean pH, we're talking about quite small changes, but they're small changes on this scale. So you'll see here some common solutions that you'll be familiar with. Battery acid, for example, right on the acidic end of the scale, pH 0 to 1. And then on the basic end, we have things like oven cleaner and drain cleaner, which are alkaline solutions. You'll notice Coca-Cola up there at pH 3, so a very acidic drink. If you haven't found a reason to boycott Coca-Cola yet, there's one for you. And distilled water is neutral pH. And you'll see just under that is seawater, which has a slightly alkaline pH of around 8. That's important to bear in mind as well, because when you talk about ocean acidification, it almost makes it sound like the oceans are acidic. They're not acidic, they're alkaline, but they're becoming more acidic through these changes in pH. So the chemistry is a little bit complicated when you get into the depths of it, but this is a very simple representation of it. So basically what happens when CO2 dissolves in seawater, it bonds with water, and then it forms this species carbonic acid, which then undergoes these various dissociation reactions. And basically you end up with hydrogen ions. You can see the hydrogen ions on that graph. And that's what causes the acidification. That's why CO2 in the atmosphere leads to ocean acidification, which is an increase in the concentration of these hydrogen ions. So how does it look? Pre-industrial values, the oceans had a pH of around 8.2. Modern values today fall somewhere between 8.0 and 8.1. That sounds like nothing, right? That's what I mentioned earlier, this logarithmic scale. But that actually corresponds to around a 60% increase in the concentration of protons in seawater, or hydrogen ions. And by 2100, it's expected to fall further to 7.6, which by that point will correspond to a near 300% change in the acidity of seawater. These changes are very, very gradual from year to year, so you actually need really long time series to be able to show this in marine systems. And there are only a few of those that exist around the world. The closest one to us and the most relevant is one in Iceland, which started in 1985. And you can see from this graph that the pH has been steadily declining over that 30-year observation period and has dropped by around 0.1 pH units. But you need a lot of observations. You can also see the variability on that graph as well. It's also important to note that these changes are not going to be the same all over the globe. Some areas are anticipated to become acidic or more acidic quicker than others. So what this shows is the relative change in ocean acidity compared to the 1990s by the end of the century. And the darker red colors show those areas that are likely to experience more acidification. And you can see in the north, in the North Atlantic and the Arctic, those are the areas that are likely to become more acidic. That's right where we are. Partly that is due to colder temperatures in these areas and freshwater input. So gases are typically more soluble in colder water, so there's more CO2 going into the system. And there's a lot of freshwater input from Arctic rivers and ice melt, which changes the capacity of seawater to buffer against these changes. So why is this relevant, and why is it relevant for the Faroe Islands? That's because of its impact on biology. This primarily affects organisms that build shells and structures out of calcium carbonate. And that covers a whole range of organisms, so many different species of marine plankton. They build shells out of calcium carbonate. And it's important to remember that these are the base of the marine food web, so all life in the ocean is completely dependent on these, including fish. And then corals as well, they also use calcium carbonate, and these are important habitats and nursery grounds. And then there's some experimental evidence to show that there's a direct impact of ocean pH on juvenile fish. So before fish develop gills, they don't actually have the ability to regulate their internal pH, so they're completely susceptible to the pH of their environment. So the experiments that have been done showing or subjecting juvenile fish to increasing levels of ocean acidification show a much lower survival rate as pH drops before they develop their gills. It does not affect adult fish so much. So how do we measure this? It's incredibly difficult to actually measure this reliably. Here there are kind of 4 parameters that are important to know about. One is PCO2, which is the partial pressure of carbon dioxide. That's the amount of CO2 as a gas that's in equilibrium with seawater. Then there's pH, which we've already discussed, the amount of hydrogen ions in seawater. There's this concept called total alkalinity, which is somehow the buffering capacity of seawater. You can think of that as like a sponge that can soak up these acidic properties. And then total dissolved inorganic carbon. So all of those 4 things can be measured analytically. And that's important for this indicator because every time you try to measure one of these things, it has a certain level of analytical uncertainty associated with it. And you can kind of constrain what that is by analyzing reference material. And I've actually kind of changed the way that we've been measuring this at Havstovan, because originally we were measuring total alkalinity and dissolved inorganic carbon, and then you can kind of calculate the other values, so ocean pH. But this is very, the instrument to do this is very unreliable, and the data that was coming out was not very good, and I was just not very satisfied with the sustainability of this approach, and also it was very inefficient time-wise. So we've actually changed now, and we've developed methods, or implemented methods, I should say, to measure pH directly and also total alkalinity. So the way this indicator works is that they have defined 3 different categories depending on the quality of data that you produce. So one which they call climate quality, and in their own documentation, the UN mentioned that this is only achievable by a few specialist labs throughout the world. And then something they call weather quality, which they report most competent analytical labs should be able to produce data in this category. And then this 3rd category, which is undefined, which is specifically aimed at countries that are just starting to get into making these measurements and to build capacity in the hope of moving up to the others. And that's kind of where we started, obviously, some years ago. Those numbers are not so relevant, but, well, they are extremely relevant, but you don't have to remember them. But they are basically the constraints that this indicator have put on. So you can see the precision that we're looking at here is like 0.04% on a measurement. So any of you that have done analytical chemistry will appreciate just how difficult it is to get that level of precision. The old methods that we were using had a precision of about 0.1 and 1%, which put us in this undefined category. So we were not even actually in a position to report this data as part of the indicator goal. But these new methods are much better, they're much more stable. So for pH, we're actually up in the climate category now. We have a precision of less than 0.03%. And for the alkalinity, we're right on the border between climate and weather. So we have a precision of 2.5, and you need to be less than 2 for the climate. So we've drastically improved the methodology, and now we're producing data that can actually respond to this indicator. And as I mentioned, part of the reason that you need such good precision on these measurements is because the changes are so small. We're talking about changes that are 0.04% per year, so we need a precision that's much better than that. That's why it's less than 0.03%. So how do we measure this? We measure this as part of our kind of oceanographic survey work, where we go out with our research vessel 4 times a year and we run these transects away from the Faroe Islands, measure a whole range of chemical, physical, and biological properties of seawater. And at some of the stations we've selected for sampling for carbonate chemistry to measure ocean pH. So the ones I'm just highlighting today is N14 in the north and N4 and V6. And these are important because they're subject to different water masses. So you can see N4, for example, is receiving influence from this kind of Arctic water coming towards it, and so forth. So here's just kind of a glimpse of some of the data at these 3 different stations. So this shows measurements that were made in 2017 at these 3 stations, and measurements that were made in 2023 in orange. And you can see at all 3 of those stations we measure lower pH now than we did 6 years ago. So we actually can also detect this ocean acidification trend in Faroese waters. And when you do the calculations, they correspond to a change per year on the order of, for N14 and V6, between 0.03% and 0.05%. So that's actually in line with this prediction of 0.04% per year. And at the station N5, the change is actually much higher. So either that's because these measurements that were made initially are not good enough data quality, but that's the same case for all the stations, or that's experiencing bigger changes because it's subject to Arctic water. So to summarize, for indicator 14.3.1, ocean acidification is a pressure resulting from climate change that we're also experiencing in Faroese waters. We've now developed methods that meet the stringent data requirements for indicator 14.3.1, and our preliminary analysis shows that acidification is progressing in Faroese waters at the expected rate and perhaps even a greater rate than predicted. Recommendations for the future: we don't have good measurements in the shelf system, landgrunnen, because we require many more measurements to do that. It's a much more variable system, and that's just not tractable with the way we do it, so we need to invest in newer technologies like sensors and automated samplers in order to get the right amount of data to do that. So yeah, thank you for your attention.